In this video, we're going to talk about the overtones and the fundamental overtones, the second overtones, but just to give you a quick recap on what we did in the previous video of stationary waves and phase difference. I'll just go over it, seeing as the next bit's probably not going to take us a good 5-15 minutes. So yeah, so the phase difference was the difference between two vibrating particles, and it's the difference between the wave. So yeah, along in comparison to the wavelength even. So say this is a wave. Again, I did go over this in the other video, but it might be beneficial just to go over it again, because I did do it a bit fast. So this is the wavelength for this lambda, and let's choose, I don't know, this point here, middle, and this is half a lambda. I'm going to give a thing for lambda, meters in a minute, and then this is a quarter of lambda. And you want to know the phase difference between these 2 points. Well, actually it's going to be a quarter. Well, anyway, so, okay. Yeah, that's going to be a half, and then that's going to be a quarter. Sorry, half, yeah. And let's give lambda equals 2 meters. So I don't know if you can see that very well, but hopefully you can. Lambda equals 2 meters, so 2 meters, 1 meter, half a meter. Just putting this in comparison. So a quarter of a lambda is half a meter. This is a fundamental overtone, by the way. Sorry, first overtone. So, because it's sort of got two halves to make one wavelength. Okay. So, as we said before, the phase difference is 2 pi over d. Sorry, 2 pi d over lambda. So, as this is a quarter, let's do the phase difference for this one. Should have got a calculator. Alright, I'll leave this. You can do it on your calculator if you want to find out the actual phase difference. So 2 pi d over, let's call this A, let's call this B. So A, 2 pi times, that's half a metre, so times a half. Now it's got to be in metres, over 2. So that means pi, oh, it should be d, yeah. So pi over 2 equals half pi, which equals 90 degrees. So that is 90 degrees out of phase, that A. Okay, see that? See how I got that? So, yeah. Hopefully you've seen how I've got that. If you don't understand why it's 90 degrees, just, again, send me a link and I'll answer your question, because everyone might have a different view of how they see me do that. And then B, that's half a wavelength. So that means it's 2 pi. So that's A. That's B. That's not part A and B of the question. That's just A and B respective of the vibrating particles. So 2 pi d over lambda equals 2 pi. The distance is half of 2, which is 1, times 1 metre over 2 metres. That means it's equals to pi, 180 degrees out of phase. Now the reason why I picked quite simple things is to show you how clearly you can know if you're right or wrong. Now, if one wavelength is a full turn, if you like to think of it like that, then the two ends, if one's at the front and one's at the end, then it's going to be maximum out of phase. So that's going to be 360 degrees out of phase. So if it's halfway, half 360, 180. So the particle between the first and the middle particle is going to be 180 degrees out of phase. Hence B on the first particle is 180 degrees out of phase. And then A, because it's a quarter of the way, is half of 180, so that's 90. So that's why it's 90 degrees out of phase, because it's a quarter of the way along to 360 degrees. Yes, 90 is a quarter of the way to 360 degrees in terms of being out of phase by that much. So we could say that the first particle and B would destructively interfere because they are 180 degrees out of phase, and if we were to demonstrate that on the Young's fringes, then that would be a black spot on the fringe. However, A and B together, between them, is 90 degrees out of phase because there's a quarter of the wavelength between them. So that's the same as the wavelength. Yeah. Hopefully you've got that. If you don't, I said, give me a shout and we'll go over it. And I'll create another video in response to your comment and we'll go over it together. So you can ask me any question you want and I'll happily go over it. So the final and last part of waves, and it's all done, is the part this video was actually about. And this was the fundamental first to second overturn. So, as we know, just before we draw any waves at all, we know that C is equal to F lambda. So, just to make sure there's no other equation. So our first thing is going to be the fundamental. The shortest one you can have is where it's half a turn, and then that means the wavelength. So that's L. Let's call that the length of the wave. Now to make a whole wavelength, that is only half of a wavelength because it's got to come back up the other side if you imagine it like that. So it's only half the turn. So if you imagine a full wave has to go down, then up. That's only gone down. You need to go up. If you can imagine that. Pretty weird, but still. That's only gone half the way. So it's only half of a wavelength. So if we're giving L is equal to half the wavelength, we need to times it by 2 to get a full wavelength. Therefore, the wavelength is 2 times L. So that's L, it could be 1.2 metres. To get the wavelength, you need to times it by 2. So the wavelength is equal to 2L. So as we said before, C equals F lambda. And if we know lambda is equal to 2L, if we rearrange it to get F, we wanted to find F. So we know lambda is equal to 2L. So C equals F times 2L. And if we wanted to find F, you could do F equals C over 2L. Hopefully you saw how we got that for that one. And hopefully that did seem quite obvious. This next one's a bit more easy to understand. This is the one where we draw a full wavelength on the table, whiteboard. I'm just going to keep drawing it in particles, so you see where we got the phase difference from. So this is a full wavelength. This is L, and L is equal to the wavelength. Because, as I said, it needs to go down, then up. And that's going up, then down. Which is the same as going down, then up. But, yeah, so that's a full wavelength. Because it's got 2 nodes at either end, and a node in the middle, and 2 antinodes. That is the... Yeah, so a wavelength has to have 3 nodes. So, one at the start, one in the middle, and one at the end. And 2 nodes, one at the first quarter, and one at the third quarter. So it'd be a full wavelength, which satisfies our wave there. So as you can see, the antinode, there, antinode, there. So if you think of node as 0 displacement, an antinode has to be the opposite, maximum displacement. So it's the amplitude, which is the maximum displacement. You see how we're linking all this in. So that gives us the antinode. And as we said before, C equals F lambda. So this is very simple. So it's just F equals C over L. Because L is equal to lambda, so we just swap L's lambda to L into the equation above, and then that gets us F equals C over L, which is what it says in the book. Now the next one's a bit more confusing. I mean, they are likely to ask you, there are more ways, there is a way of working out, you know, when it's second, third, fourth, fifth, sixth, seventh, etc. But they're not going to ask you past third, so I'm just going to keep it simple for you. You probably won't, but you can just work it out by drawing an extra overtone. An overtone is half added on, so fundamentally it's half. First overtone is half plus half is a whole wavelength, and then the so then second overtone will be 1 plus a half, which is 1.5 coincidentally. So that's 1.5 of a wavelength. So let's draw that. So you've got our standard line here at the bottom, which you always draw. So it starts here. Sorry, should have drawn that for the other one, but it doesn't really matter. So, as we said before, we can see this whole wavelength. Yeah. So this is the length of it, and this is a full wavelength. Don't know if I've done that very well. Yeah, sorry, I haven't done that very well, but hopefully you've seen where we're going with this. And this is the, yeah, so that's two progressive waves on a string, just demonstrating it for you so you can see where we're getting the wavelength from. Hopefully you can see that. If you can't, I'm sorry, just trying to help you out there a little bit. So the wavelength, the lambda, is equal to 2/3 of L. Now it's not going to fit into our simple equation of C equals F lambda to make F equals to C over lambda, as if our lambda is 2/3. 2/3 of L. So we can substitute that in, times it, mess around with it to simply get 3C over 2L. That is just, I'm not going to do the expansion etc, but that is how you do it. So yeah, that is basically all of it wrapped up. Yeah, so God's sakes, right, so the time taken for the wave to travel on the string and back equals, so T equals 2L over C. Oh, it's just doing one equation there. Right, I'm going to quit this now because I'm running out of room. So hopefully you can pause the video now and have a look at that. And I'll see you in the next videos.